Chapter 13.1 Testing the variance of a single population. In Chapter 12, we introduce the chi-square distribution to conduct a variety of hypothesis tests that involve comparing proportion, performing goodness of fit tests, and testing for independence. We will once again rely on the chi-square distribution to perform a hypothesis test for a single population variable. We'll consider both one-tail and two-tail tests. One-tail hypothesis test for a single population variance. We will start this section by referring back to Chapter 9 and our horrific experience with the new self-serve checkout system being tested at our local grocery store. Suppose the store manager have decided that if the standard deviation for the time required by self-serve customers to check out is less than 2 minutes, additional self-serve system should be installed at the other location. A standard deviation of at least 2 minutes would be one indication that some customer, such as our outer, struggle with the self-serve system and take much longer to check out than other or normal customer. To test if new system should be installed in other store, the checkout time in minutes of 24 randomly selected self-serve shopper were recorded and are shown in Table 13.1. This data can also be found in the Excel file checkout-time.llxx. Using this sample data, we will conduct a hypothesis test to see if the population standard deviation for the checkout time of customer is less than 2 minutes. Step 1. Identify the null and alternative hypothesis. The store's goal is to achieve a standard deviation of less than 2 minutes. Because we do not have a procedure to test for the standard deviation directly, we need to convert the standard deviation of 2 minutes into a variance by squaring it. 2 squared equal to 4 minutes squared. This results in the following hypothesis. Null hypothesis, sigma squared is greater or equal to 4. Alternative hypothesis, sigma squared is less than 4. The goal that the store would like to achieve. Step 2. Set a value for the significant level alpha. The significant level has the same interpretation for this test as it has had for previous hypothesis tests regarding the mean and proportion. The value of alpha represents the probability of a type 1 error, which occurs when we reject a null hypothesis that is true. For our self-serve example, a type 1 error occurs when we conclude that the population variance is less than 4 minutes squared, when in reality it is 4 minutes squared or more. Let's conduct our hypothesis test using alpha equal to 0.05. Step 3. Calculate the chi-square test statistic, x squared. The test statistic for a one-sample variance test, or x squared, is shown in equation 13.1. Where x squared is the test statistic, s squared is the sample variance, sigma squared is the population variance expressed in the null hypothesis, and is the sample size. We first need to calculate the sample variance, which can be done in one of two ways. Recall that we studied the sample variance way back in Chapter 3. The equation for calculating it is repeated here as equation 13.2. To use this equation, we need to sum up the values or sum of xi and sum up the square of the values or sum of xi squared from table 13.1. These results are as follows. Summation of xi is equal to 4.4 plus 3.9 and so on equal to 100.2.9. Summation of xr square is equal to 4.4 square plus 3.9 square plus 4.2 square and so on is equal to 490.55. Recognizing that we have 24 observations in our sample, or n equal 24, our sample variance S square is as follows. S square is equal to 2.146. We can also rely on the Excel function equal to var.s inside parentheses the data values. It will provide us with the same result. Now that we have our sample variance, we plug the remaining values into equation 13.1 to get the following test statistic. X squared is equal to n minus 1 times S squared divided by sigma squared is equal to 24 minus 1 times 2.146 divided by 4 equal to 12.34. Step 4. Determine the chi-square critical value, x squared alpha. The test statistics shown in equation 13.1 follows the chi-square distribution that we introduced in chapter 12 with n-1 degrees of freedom. Table 13.2 shows an excerpt from table 8 in appendix A, which shows the chi-square critical values. Row 1 to 22 in this table have been hidden to conserve space. That this is a lower or left tail test because the alternative hypothesis, or H1, is expressed as less than 4. This put the rejection region with area alpha equal to 0.05 on the left side of the distribution and leave 95% of the distribution to the right of the critical value, also known as the right tail. The column in table 13.2 are based on the area in the right tail of the distribution. So we look for the column labeled 0.95. We also have n-1 or equal to 24 minus 1 is 23 degrees of freedom for this example. According to the table 13.2, the critical value x squared alpha is equal to x squared 0.95 is equal to 13.091. We can also use Excel chi-square.inv.rt function to determine the chi-square critical value, which has the following characteristic, equal to chi-square.inv.rt inside parentheses right tail area, comma, degree of freedom. For our checkout time example, we have chi-square.inv.rt inside parentheses 0.95, 23 equal to 13.091. Step 5. Compare the test statistic x squared with the critical value x squared alpha. Figure 13.1 shows the rejection region for the self-serve checkout example along with the critical value and test statistic. Test statistics x squared equal to 13.34 is less than x squared 0.95 equal to 13.091 and lies in the shaded region, rejection region. Stage 4. State your conclusion. By rejecting the null hypothesis, we have evidence that the population variance for the checkout time is less than 4, which translates into a standard deviation of less than 2 minutes. Because we have rejected the null hypothesis, the decision should be made to install additional system in other location. The chi-square test for a variance does have an important requirement. The population from which the sample is drawn need to be normally distributed in order to get valid result. This requirement holds true for any sample size and is fairly rigid. In other words, moderate deviation from a normal population can result in unreliable conclusion about the population variant. Chapter 12 demonstrated a method to test if a population follows the normal probability distribution. Two-tailed hypothesis test for a single population variant. Now that you have mastered the one-tailed variant test, let's move on and examine the two-tailed procedure with the following example. As we learned in the beginning of the chapter, refrigerator manufacturers design their unit to maintain temperatures within a certain range. Too much temperature variation can result in food freezing or spoiling prematurely. Too little temperature variation can lead to higher energy costs because the refrigerator compression cycle on and off more often than necessary. Suppose Amana, a major refrigerator manufacturer, has been trying to achieve a standard deviation equal to 4 degrees of Fahrenheit for a particular model. To test this variation under normal conditions, the refrigerator was filled to 75% capacity with food and was opened 30 times during an 8-hour day for 10-second duration. The table 13.3 shows the temperature reading recorded during this experiment. This data can also be found in the Excel file refrigerator.xlsx. Using this data and alpha equal to 0.05, Amana would like to perform a hypothesis test to determine if the standard deviation of the temperature for this particular model is equal to 4 degrees Fahrenheit. Step 1. Identify the null and alternative hypothesis. Amana's goal is to achieve standard deviation equal to 4 degrees Fahrenheit. This translates into a variance of 4 squared equal to 16 degrees Fahrenheit. Because we are testing for equality, this is a two-tailed test. So therefore, the hypotheses are null hypothesis, S squared equal to 16, or this is the goal that Amana would like to achieve. Alternative hypothesis, S squared not equal to 16. Step 2. Set a value for the significant level alpha. Amana set alpha equal to 0.05 for this hypothesis test. Step 3. Calculate the chi-square test statistic, or X squared. For this example, we are going to take the easy way out and use Excel to calculate the sample variant. Using the var.s function on the dataset, we will get the following. X squared is equal to S squared equal to 19.151. Using equation 13.1, our test statistic is as follows. S squared equal to n minus 1 times S squared divided by sigma squared equal to 30 minus 1 times 19.151 divided by 16 equal to 34.71. Step 4. Determine the chi-square critical value, X squared alpha. Because we have a two-tailed test, there are two critical values, one in each tail of the chi-square distribution. The area that corresponds to alpha 0.05 is split evenly, so alpha divided by 2 equal to 0.025 between the two tails of the distribution. The left or lower critical value has an area equal to 0.025 to its left and 0.975 to its right. Look back at table 13.2 under the area and the right tail of distribution equal to 0.975 column and the degree of freedom or rho n-1 equal to 30-1 equal to 29. Here we will find that the left critical value is alpha square, x square alpha equal to x square 0.0975 equal to 16.047. The right or upper critical value is an area equal to 0.25 to its right. In the table 13.2, look for the area in the right tail of distribution equal to 0.205 column and the degree of freedom rho 29. Here we will find the right critical value is x square alpha equal to x square 0.205 equal to 45.722. Both of these critical values are shown in figure 13.3. Using Excel chi-sq.inv.rt function, we can confirm the chi-square critical value for our refrigerator example. Chi-square for 0.975 with degree of freedom 29 equal to 16.047 and chi-square for 0.025 with degree of freedom 29 is equal to 45.72. Step 5. Compare the test statistic x squared with the critical value x squared alpha. Figure 13.3 graphically illustrates the test statistic and the rejection region for the refrigerator example. Because x squared equal to 34.71 is between x squared 0.975 equal to 16.047 and x squared 0.225 equal to 45.72, we fail to reject the null hypothesis according to figure 13.3. Step 6. State your conclusion. By failing to reject the null hypothesis, we do not have evidence that the population standard deviation is not equal to 4 degrees Fahrenheit. Because we can never accept the null hypothesis, we cannot conclude that the standard deviation for this population equal to 4 degrees Fahrenheit. However, we have a business decision to make here, which is to A, decide that the population standard deviation is acceptable, that is equal to 4 degrees Fahrenheit, or B, decide that the population standard deviation is unacceptable, that is not equal to 4 degrees Fahrenheit. When we put on our business person hat the result of this hypothesis test, let us to choose option A and conclude that the refrigerator design is working properly for this particular model. We know this might seem like a contradiction, but choosing to find support for the null hypothesis in this example is the appropriate business decision. As we mentioned earlier in the chapter, the people who conduct quality control program are very interested in the variance of a process because it is measure of consistency. Generally speaking, more consistency or low variance is more effective than less consistency, high variance when dealing with a business process. However, variances that are much lower than expected can be an indication that something has gone wrong, which merit further investigation. One explanation may be that the measuring device has malfunctioned. Thank you.